Hi everybody, in today's video we're going to be analyzing graphs of parent functions. So we're going to be looking at how to evaluate a function, how to determine symmetry, and we're going to be doing some more work with domain. So a function is a relation in which each element of the domain is paired with exactly one element in the range. All right, so let's see, what exactly do we mean by exactly one element in the range? So for example 1, it says determine whether each relation is a function, right? And if you take a look at letter A, you can see that this -2 value in the domain is related to two different values in the range. So that doesn't meet the requirement of a function that has to have exactly one element in the range, okay? -2 goes with -1, and it's also paired with 3. So letter A is not a function. We'll just make a note here. -2 has two outputs. All right, now if we take a look at letter B, each element in the domain is paired with exactly one element in the range. Right? Nothing has more than one output. So this one is a function. A vertical line test is defined as at any given point on a graph, you can draw a vertical line and it will only intersect with the graph once if the graph is a function. So this is a really easy way to determine whether or not a graph is a function. You drop a vertical line, think of it as like a little fishing line that you drop. And anywhere you drop that fishing line, it should only hit the function in one place. So letter A, that line will only hit the function in one place. In letter B, notice that it's hitting in two places. So this one is not a function. And the same with the last one, hitting it in two places, so not a function. It can only hit the function in one place. All right, function notation. F of x. That's read just the way you see it here. F of x. And I end up saying it really fast, F of x. Right? So I just wanted you to see it kind of spelled out. And it does not mean that you're multiplying f by x. No, no, no. All right? We have an example in this box right here of function notation. Right? F is the name of the function. X tells you that x is our input. And the 2x part here in this example tells you what the function does. So here's an example. Evaluate f of 4 for the given function. What does that mean? That means take 4 and substitute it in for x in the function. All right, so far so good, hopefully. We're going to do a little practice. Evaluate f of 2 for the given function. So we're going to replace wherever you see x in the function, we're going to replace it with a 2. So what you may want to do with these is just sort of highlight what's going to be replaced. And then we go ahead and solve that. So in this example, f of 2 is equal to 2. We're going to replace, for number 2, we're going to replace x with 4, f of 4. Square root of 16 is 4, so we end up with 1 over 4 minus 1, so we get 1/3. All right, so for the rest of these, I would suggest pausing and then coming back and checking your work. F of 3 equals 2 to the third plus 3. So f of 3 is equal to 11. Okay, number 4, it says replace x with x squared. So nothing changes, it just looks a little more intimidating. So we're just going to replace x now with x squared. Not a big deal, don't get too worried here. Just replace x with x squared. So we just end up with 2x squared minus 4. There's not much more you can do with that. And for fun, I added another one that maybe looks a little scary. We're going to replace x with x plus 1. So wherever we see x in the function, we're replacing it with x plus 1. F of x plus 1. We're replacing x with x plus 1. We've got 2 x's in this function, so we've got to replace x again with x plus 1. And then we're all set. If you really want to have some fun, you can multiply that out, but we're going to leave it as is. All right, we're going to talk a little bit now about symmetry. When we discuss symmetry, you're either going to have an even, odd, or a neither function, okay? We're going to look at even first. So the graph of an even function is going to be symmetric about the y-axis. And we've seen this before. We examined this in lesson 1 when we looked at the absolute value of x. So we'll just go ahead and do a rough sketch of that graph. Can you fold the graph in half along the y-axis and it aligns perfectly? If so, it is even. And we can for this particular graph. An odd function. The graph of an odd function is symmetric about the origin. An example of an odd function is y equals x cubed. So it says, can you flip the graph over the y-axis and then the x-axis and it still looks the same? If so, it is odd. So if we reflect the graph over the y-axis, and I'll try to do this here. So here's a reflection of the graph over the y-axis, right? Takes care of that. And then we reflect it again over the x-axis. Let's see, we'll do that in blue. We're going to end up with that graph, and it still looks the same. So in this case, this function is an example of an odd function. So at this point, we're going to do a little practice. Determine if each graph below is even, odd, or neither. Justify your answer by stating how the graph is or isn't symmetrical. So if you're saying it's even, you would say that it is symmetrical over the y-axis. And if you're saying it's odd, you would say symmetrical over the origin, or you just say neither, not symmetrical. All right, so pause the video, give these a shot, and then come back. For number 1, we already know that, okay, for number 1, we have y equals x squared. This guy is even. And it's symmetrical over the y-axis. For number 2, this one is odd. Now it's going to reflect over the y-axis. And then it's going to reflect again over the x-axis and be the same graph. So we would say that this is symmetric over the origin. For number 3, we don't have any symmetry. It's not going over the y-axis or the origin. So this would be neither. And for number 4, we have odd. It's symmetric over the origin. Right, so if we reflect over the y-axis, and then we reflect again over the x-axis, we end up with the same graph. All right, so that's really the easiest way to determine symmetry, just by looking at the graph. Now, if you're not sure, you can also do it algebraically. If you put a negative x, if you replace x with a negative x in the function, and you end up with the exact same function, it's even. If you replace x with a negative x in the function and every sign changes, all of them change, it's odd. So let's look at some examples. All right, so I'm going to replace x with negative x. And I'm going to simplify it after I do it. Now, anytime we have a negative number raised to an even power, it becomes positive. So I can just rewrite this first term like this. So we get 3x squared plus 8. Well, it didn't change at all. Every term, the sign remains the same. So this is an example of an even function. And let's just make a note, no signs changed. All right, let's try it for the next one. We're going to put a negative x. We're going to replace x with negative x everywhere in this function, and then we're going to simplify it. All right, so we have a negative number raised to an odd power. That's going to remain negative when I take away the parentheses. And then we have a negative 4 times a negative x. That gives me a positive 4x. Now let's compare. Here's our original. The first term was positive, the second term was negative. Once we put the negative x in, the first term changed to negative and the second term changed to positive. So every sign changed. So that means this one is odd. Every sign changed. So this is odd. All right, let's try one more. Replacing every value of x with negative x, and then we're simplifying. We have negative x squared, that just becomes positive because any number squared, right, is going to be a positive number. Negative times a negative is positive. All right, so this term was positive, it stayed positive. This term was negative, it changed to a positive. So either every sign changes or no sign changes. And so here we've got some signs changing and others did not. So this is a neither. So I'm just going to make a note here. One sign changed. The others did not. And this would be neither. Okay, you have a chance to try it on your own. You have 4. Pause the video, try them, and come back to the video. Okay, check your answers. Make sure you've simplified, compared every sign, and now we're going to move on. Next, we're looking at interval notation, and we did a little bit already in lesson 1 with interval notation. We're just going to, review it again here. We're going to keep reviewing it until you feel comfortable with it. We have some examples when we're not including values. We're going to use parentheses and open circles. When we are including values, we're going to use filled in circles, all right? You may want to just take a quick look at these bullet items. We'll talk through them very swiftly here. It's a concise and easy way to express a range. It's like shorthand for intervals. Brackets are inclusive, parentheses are exclusive, a comma equals up until, U is the union sign. We would have a minimum and a maximum in our interval. And infinity and negative infinity always get parentheses because you cannot equal them. Infinity is a concept, not a number. All right, so let's do some examples here. We'll do A and B together, and then maybe you want to pause the video and try to do it on your own. So we're being asked to write the below examples in both interval notation and then draw the interval on a number line. All right, so in this first example, x is greater than 4, but notice it's not greater than or equal to 4, it's just greater than 4. So that means we're going to start at 4 but not include 4 and go to infinity, and infinity always has a parenthesis, not a bracket. Now we want to draw the interval on a number line. All right, so I'm just going to mark anywhere on this line 4. You don't need to put any other numbers. All right, we're saying that it's an open circle because we don't include 4 and it's greater than 4. Done. All right, letter B, we have x is less than 2. All right, so we want everything prior to 2, negative infinity up to 2, but not including 2. Mark 2, open circle, goes to the left. Letter C, x is greater than 4, or x is less than or equal to 2. Okay, so let's start on the left side when we talk about this guy, because we say x is less than or equal to 2. So we want from negative infinity to 2, including 2, or union from 4, not including 4, to infinity. And then we'll do our number line. We've got 2 and 4 represented. So we want everything including 2 and before it, and everything from 4 not including 4 to infinity. All real numbers. Okay, I think you're already familiar because we did this again in lesson 1. I might just put a 0 here, but really this is how we would represent that on the number line. All right, letter E. It says x does not equal 3. X equals everything but number 3. So that means we're going from negative infinity to 3, not including 3, or from 3 all the way to positive infinity. So everybody but poor old 3. Everybody before 3, everybody after 3. Letter F, x is greater than or equal to negative 2 and less than or equal to 2. So we are including negative 2 as our minimum, 2 is our maximum. Plot that out. So it's everything between negative and 2 and including those values. Including means we're going to shade that and connect. Done. Okay, very short, sweet, to the point lesson. Hope you enjoyed it. Thanks for watching.